B would get a meaningful, clear message. Assume that someone else is sending a message on behalf of A, and then B can clearly identify that the message was sent by someone else and not A, because B would be using A's public key to decrypt. So, if someone else has sent a message, the probability of B getting a legitimate, meaningful message is very low. Key usage for authentication. Here is another way of authentication. The sending message is being encrypted by using the private key of the sender, and the receiver uses the sender's public key to decrypt the message. It has been identified that public key cryptography allows us to do confidentiality necessary transactions in secure infrastructure like internet in a very secure manner. Applications. When talking about the applications in public key system, there are mainly three categories: encryption or decryption. Here, the sender encrypts a message with the recipient's public key. Second category is authentication, also can be called as digital signature, where a sender signs a message with its private key. Third type is key exchange. Here, two sides cooperate to exchange a session key. Requirements. Some of the requirements for public key cryptographic algorithms are: it should be computationally easy for a party to generate a key pair. Secondly, it should be easy for the sender to generate ciphertext and easy for the receiver to decrypt it. Further, it should be computationally infeasible to determine one key knowing the other. Similarly, it should be computationally infeasible to recover a message by just knowing the public key and the ciphertext. Lastly, the two keys should be interchangeably used for either encryption or decryption. Here we will be discussing about one of the public key algorithms, which is known as RSA. The RSA public key algorithm. RSA is the most widely used algorithm nowadays. Up to today, no defect is found in RSA. The popularity for RSA is due to its flexibility and power. This was developed in 1977. The name RSA comes from the first letters of the names of its inventors, Rivest, Shamir and Edelman. RSA uses a block cipher and the size of the blocks dependent on the user. RSA key generation. This slide explains the RSA algorithm, which creates the public and private keys. As the first step, two prime numbers are selected randomly as P and Q. Then calculate the product. As a third step, calculate P minus 1 into Q minus 1, which is denoted as phi n. Phi n has a significance. It also called Uter-totient. It represents the number of positive numbers less than n and relatively prime to n. Then we select the integer e, where integer e is relatively prime to phi n, which means the GCD of phi n and e equals to 1, and e should be a number between 1 and phi n. As the fifth step, we need to find d, where d is the inverse of e modulus phi n. Then we can define public key as a combination of e and n, and private key as a combination of d and n. This method seems to be very simple, but the typical secure RSA version today uses key sizes 1024 bit or more. Therefore, you would get very large numbers for n. RSA encryption. In RSA encryption, the size of the plain text M should be always less than n. N is the same which was defined before, and ciphertext C is equal to m to the power of e modulus n. Even though the equation looks much simpler, the processing is not so, as n and e are very large numbers, so that in RSA encryption we need efficient processing. RSA decryption. Here, in the process of decryption, to decrypt the ciphertext C and convert it to plain text M, you may get C to the power of D modulus N. Example. Here is an example illustration of the RSA algorithm key generation process. Here is the example illustration of encryption and decryption process. In the decryption process, you can see that 66 to the power of 77 is a very large number, and the question is how to calculate this number. Here you may use multiple precision arithmetic libraries where it has the ability to store, manipulate and maintain very large numbers. The security of RSA. When considering the security of RSA, it is clear that RSA is very secure since we use large numbers of bits in E and D. Still, there is a problem of factoring n into two prime factors. This problem still cannot be computationally tracked. The third point is that in RSA, the key sizes are ranging from 1024 to 2048 bits. This range seems to be very safe today. Most of the financial transactions carried out through internet uses the key size 1024, but in case if you feel that it is not safe, you further increase the key size. Until recently, the keys with the bit range 300 seem to be quite secure, but a worldwide team cooperating over the internet using 1600 computers recently cracked the code in 8 months. Whenever a bit is increased, the number of combinations become double. Therefore, 1024 bits key size is considered to be highly secured and strong even during the next 10 years. Now let us discuss about Diffie-Hellman key exchange. Diffie-Hellman key exchange was primarily used for sharing a key between two parties but not using RSA. This method was proposed in 1976. This does not use encryption or decryption and allows a group of users to agree on a secret key over insecure channel. In this method, the key is generated by using some numbers. These numbers are being shared through internet and even the intruders can see. But the beauty of this method is that even if the intruders are aware of the numbers shared, he can't generate the key. This method depends for its effectiveness on the difficulty of computing discrete algorithms. The Diffie-Hellman process can be explained as follows. Assume that there are two people as A and B and they want to agree on a secret key. Firstly, they agree on two large numbers n and g. Then A chooses a random number x and computes p, where p equals g to the power x modulus n, and sends p to person B. B also does a similar calculation and sends Q to person A. Finally, A computes K1, where K1 equals Q to the power x modulus n, and B computes K2, where K2 equals P to the power y modulus n. Then it can be seen that K1 equals to K2. The same process is expressed here in this pictorial view. Let us now discuss about the advantages and disadvantages of Diffie-Hellman algorithm. The advantages of Diffie-Hellman algorithm are: it needs no prior communication between A and B. Secondly, security depends on difficulty of computing X. Choices for G and N are critical. The only disadvantage is that this is susceptible to intruder in the middle attack. The C language implementation for encryption and decryption of RSA algorithm is as follows. Man in the middle attack. The man in the middle attack can be expressed pictorially as in the slide. Assume that A and B needs to share the numbers and an intruder is connected to the link through some node. The intruder blocks A from communicating and start to pretend as A and start communicating with B. B believes that it is exactly A and finally comes to an agreement of a key. Then B, in good faith, may send some confidential information to the intruder. Here is a comparison between symmetric encryption-decryption and asymmetric encryption-decryption. Symmetric encryption or decryption is much faster than asymmetric encryption or decryption. For an example, RSA sends data in kilobytes per second and DES sends megabytes per second. As you can see, DES is 100 times faster than RSA. So, symmetric encryption is 100 times faster than asymmetric encryption.